Today I'm going to talk about RKHS-based tests for survival analysis. So this is joint work with Arthur Greton, David Rind. He's a student at Oxford, and Dinos Zenovic. So I'm going to start with a motivation, with a clinical trial about lung cancer. We want to study the survival times of these patients, but also we have characteristics associated to these patients. For instance, some of them smoke, some of them are green, like blue, etc. So in the ideal world, what we have is that, like for each patient, we have a survival time of interest, and we have a d-dimensional set of covariates. So our goal is to test non-parametrically the hypothesis of independence between survival times and covariates that can be formulated as testing whether the joint distribution of survival times and covariate factorizes. The problem is that typically for these models, we observe other type of data. For instance, the blue man dies from lung cancer at 24 months, so we observe its survival time. But for the green man, we have that he moves to a different city after 5 months. So instead of having the survival time for that guy, we only have a lower bound for it. The same happens for the magenta man. He loses interest after 32 months, so we only have this lower bound. So what we observe in reality is this triple. TI, which is the minimum between the survival time we are interested on, and CI, which is a censoring time. We also observe this delta I, which is an indicator variable. It tells us if we are actually observing the survival time we are interested. And we observe XI, which is like a d-dimensional covariate, vector of covariates. So given this data, we want to test independence between the joint distribution of survival times, Z and X. So as you can see there, we want to test this, but we are not observing Z, we are observing TI instead. Also, for what we are going to do, we are going to assume this assumption. This is not very realistic, but without this assumption, the mathematical, the math for this problem is quite hard. So we are going to assume that the survival times are conditional independent of the censoring time given the covariates. So this is a standard assumption in survival analysis. So testing approaches, what are the challenges? The challenges are that survival times are censored. We may have high dimensional covariates. And also censoring may depend non-trivially of the covariates even under the null hypothesis. So even if the survival times Z are independent of X, it could happen that the censoring times are not independent of X. So for instance, having kids could make patients withdraw from a study because they have less time, but they are not necessarily related with the disease, how they survive. So popular approaches in survival analysis are log-rank tests, which are commonly used in the goodness of fit setting and the two-sample problem. And for covariates taking values on RD, the Cox proportional hazard model, deriving a score test for this model, it's a quite standard approach. So basically, what we do is define a parametric model for the conditional cumulative hazard function given X. The cumulative hazard function is just the integral of this hazard rate, which is the density divided by 1 minus the CDF. So we define this dependence model. And what people does is typically they derive a score test and test whether this parameter beta is equal 0. So this is quite restrictive because we are assuming a parametric model for our survival times, which is not ideal. So now we are going to do the machine learning part. So we are going to start very similarly to what people does with the score models. We are going to define a parametric model for the dependence of survival times given the covariates in terms of the cumulative hazard function. So instead of having beta X, we are going to have 2 parameters, theta, and a function omega that goes from times and covariates to R. And we're going to pick this function in an RKHS. So, but it's going to be known. It's a fixed function, different to 0, so the problem is not like trivial. And we are going to allow theta to be an open subset of R containing 0. So the null hypothesis of independence here will be equivalent to testing whether this theta parameter is equal to 0 for some fixed function omega. So because like here this becomes 1, so then like the conditional cumulative hazard function is equal to the marginal hazard function for all x. So because we have a model, a parametric model, we are going to derive a score test in terms of like the derivative of the log likelihood. And if our model is true and we are under the null hypothesis, this function evaluated at theta equals 0 should be close to 0 because this should guide this theta parameter, theta equals 0, should be maximizing the log likelihood. So just like to illustrate, here is the likelihood for right sensor data. This is a standard thing. You can like derive the likelihood. And then like derive the score function by taking the derivative of the log likelihood, like the function I show you here. So you do that, you obtain this form. And if you evaluate at theta equals 0, you get this sort of discrepancy. So right now, we cannot like really evaluate this guy because like it depends on this marginal cumulative hazard function, and we don't know it right away. But we are going to take like we are going to approximate this guy non-parametrically by the Nelson-Allen estimator, which is like the non-parametric MLE for this object. So so this thing, which looks like a discrepancy between two measures, is typically known as a log rank test. So it's like a well-known object in survival analysis, so we are going to call it log rank. So because we don't like parametric models, what we are going to do, or because like, it's not that we don't like them, it's that we don't really know which one is the good one, we are going to take supremum over like the uniball of this Hilbert space. So we are going to take all these parametric models at the same time. And if the null hypothesis is true, like this theta parameter is equal to 0, it doesn't matter what function omega you put here, this guy should be close to 0. So this seems like very difficult to compute, but it's not. Like if we pick 8, this guy as an RKHS of functions, this guy has a closed form. Like you can evaluate it exactly. You don't need to approximate it. Also, also we have like this good property that this guy can be understood as like the norm of the difference of two elements in the Hilbert space. So typically so in the sensor case, typically what people is doing in RKHS-based tests is like they take two probability distribution, they embed the probability distribution in the Hilbert space, and they compute similarity here by taking like the distance in this space. So here are two things that are important. One is like the Hilbert space, and also how we embed like our probability distribution in this Hilbert space. Because if the embedding is bad, if we map all these elements to 0, of course, it's not going to be a proper measure of like distance. But like so here in this setting, P, for instance, like we are embedding P and Q, two probability measures. So P would be like the joint distribution of survival times and covariates, and P will be the product of the marginals. So we are going to embed them in the Hilbert space, and we are going to compute like how different they are. It turns out that like we cannot do that with sensor data because we don't observe Z and X, like the survival times. We observe instead T and delta. So the measures we are embedding should be like a function of like this T and delta. So it turns out that like in the survival analysis setting, we will have like embeddings which are a bit different to those used in the uncensored case. For those people who are familiar with uncensored case, like I mean like different to the kernel mean embedding. But it turns out that our test statistic, which is the supremum of log rank tests, or can be understood as the supremum over score test, is just like the norm of the difference of these two embeddings I showed you before. So if we also, furthermore, if we pick a kernel, I haven't really explained this, but like we are using a reproducing kernel Hilbert space, which is satisfy the property which is characterized by a kernel function. So instead of like picking a Hilbert space, and that's very complicated, we just like pick like fix a kernel, the reproducing kernel of the Hilbert space. So if we pick a reproducing kernel that factorizes, our test statistic can just be evaluated very simply, like a trace. So also we find relationships with like the score test, the Cox score test. So for a specific kernel, this guy is the inverse of the Fisher information. We recover that our test is, we recover this result. Our test is like just the score test. So we study the asymptotic properties of this model. We derive the asymptotic null distribution. So it turns out like when we scale by n, our test statistic is no more than a potentially infinite linear combination of chi-square random variables. We derive like closed form for the asymptotic mean and asymptotic variance. And we have consistency results in terms that under regularity condition of the censoring, basically censoring cannot mask dependence. Because if it fully masks dependence, like we cannot like do more. But like under regularity conditions, we can like show that like we can obtain an omnibus test. Basically, power tending to 1 in infinity. And also because like typically, okay, we can find the asymptotic distribution, but the parameters are very hard to estimate. They're like, so it's impossible to use this for like defining the rejection null region. So instead, like we propose like a very economic wild bootstrap approach, like to estimate the rejection region of our test. So experiments, first we are going to study the type 1 error, like to show that our test is well calibrated. So in this setting, because like we are under the null hypothesis, the conditional distribution of survival times given the covariates is independent of the covariates. So this distribution don't depend on the covariates. But like we define different relationships with for censoring given covariates because like our censoring times can depend on the covariates. So the first two ones are independent. In 3rd and 4, we have like some sort of linear relationship. And 5 and 6 are more aggressive. We have like quadratic and exponential dependence. And this is the percentage of uncensored random variables we observe in each experiment. So these are the plots. Basically, this is like the size of the test. The alpha value is like around is 0.05. So if you see, all these curves are like centered at 0.05 as the sample size increases for all the cases. So basically, we are reaching the level of the test for our test. That's good. So I'm going to show you like power assessment, like first for continuous, for a single continuous covariate. So basically, we have two settings. The first one is like we have dependence on the covariate in the survival times in terms of the variance. As the covariate grows, the survival times start like getting more wider, like we have like more variance. And in the second one, we have like a Weibull distribution like for the survival times. And and we make the shape of this Weibull depend on the covariate. So we are going to have different crossings. So here I'm showing you like the survival times. Like in blue, there are like the uncensored ones. Like red are the censored. So whenever you see a red point, it means that there should be like a blue one above because like the red point is like just a lower bound. So this is what we obtain with our method, like for the first one for the variance. The pink one is our method, like for some kernels, like very standard kernel, Gaussian and Gaussian kernel for covariates and time. And these are like what people usually use in this in like the Cox score model. So the blue one is also our method. We show that we could recover Cox score, and we are recovering it here. The small difference are because like probably here we are using a package, and here we are using also while bootstrap. So there might be like a little difference between our results. And this is the result for the Weibull experiment. So also we have a lot of power. Recall that here we are under the alternative hypothesis, so the better, the larger the proportion of rejected, the better is our test. So also we show like a multivariate setting in which like we have a covariate belonging to RD, and we make the survival time depend only in the first dimension. So the first plot is our method in like red and green. Shows like for fixed dimension how the test power starts growing as we increase the sample size. And the second plot, it shows that like how for fixed sample size, how the power starts decreasing as we increase the dimension. And this is like, of course, we are going to see how the power decreases because like the problem is getting harder when we start increasing the dimension because like the dependency is only in the first coordinate. So, but even though we are like also decreasing like slower, like we get some signal. So, thank you.
Okay, thank you. I have two questions, actually. First is about so you have obtained the asymptotic distribution, null distribution of the test statistic, but you didn't use it, and you use bootstrapping. But, I mean, is it about the computations for bootstraps? Can you comment on that first? And the second question is about the power of the test, because the power is much higher than the other methods, but you didn't mention anything about the Taiwan error of the methods you compare your method with. Because to compare powers, the test should have, a similar Taiwan error, but you didn't mention the Taiwan error of the other methods. Can you also comment on that?
I kind of forgot, okay. Of course, those methods are well calibrated as well. It's just that, of course, we are going to win in those scenarios because, clearly the relationship here for these survival times is no proportional. So, so it's a bit an unfair comparison in the sense that, of course, the proportional hazard model doesn't hold. But when the proportional hazard model is the true model, it's generating the data, of course, probably the Cox score test will have more power than us. But what I'm trying to say is that we are more consistent. Even if we are not the best test at every possible scenario, we will be very robust. And the wild bootstrap sampling, I didn't mention here because I didn't really have a lot of time, but what we are doing is in the theory, we are doing an approximation to a degenerate U statistic. So we use sampling methods for degenerate U statistic to resample from the null hypothesis. So basically, we are saying, okay, our test statistic has it's a function of all these guys, and these guys are very ugly, but we do an approximation to something that is not that ugly and use the theory for that not so ugly thing to resample from the null.
Yes, I'm not familiar with this approach. And I just wanted to check that you have made assumptions about the distribution of the axes.
No, because that's important, but right now for my results, I'm assuming that the kernel is bounded. So integrability assumptions are kind of I'm not using integrability assumption of the kernel because basically my kernel is bounded and
Well, it seems a rather complicated approach to get a test. I mean, if you look at your hypothesis right at the beginning, that you say you're testing.
Yeah, basically here this is conditional on X. So basically basically, you will have like a distribution for the covariates that doesn't depend on, of course, on these parameters, because if not, it's just that like in the likelihood when you compute this, the parameters you are interested on are like omega and delta.
Yeah.
So that's why if you kind of like compute the likelihood for x as well.
Let's move on. Let's move on to another point. The other point is that you don't seem to get any. You don't get any estimates out of your method. It's a pure test of a null hypothesis.
Oh yeah. This is like purely test. Like we're not estimating.
Okay, in your example of the so-called multivariate survival, what did you mean when you said that only depended on the first dimension?
Oh, here it's just that like this is a vector.
Yeah.
X1 and XD, and this is like the mean. This is sampled from an exponential and only depends on X1, this guy.
Okay. Is that not the usual situation, that you would have just the survival time would be conditional on one covariate? How do you handle variable selection in your model?
That's kind of like the next step. Like first we are like building the statistical test, and like possibly we can use this test like to do variable selection. So
okay. And my final question is, what, if anything, is the advantage of your technique?
Sorry?
What is the advantage of your technique?
Of this method?
Yes.
It's just that like basically this is able to basically RKHS tests are very popular because like they work well in high dimensional settings. And they have like this non-parametric nature that like allows them like to discover like interesting relationship in the data without like following this like non-parametric, like these parametric models such as the Cox proportional hazard model. So basically the advantage is that like we are like detecting independence in a very general framework. Like we can recover other tests, but like if we assume some properties in the reproducing kernel, we have a fully non-parametric test. We are characterizing with our test like what's known as independence. So that's the advantage.
Okay, let us thank Tamara again. Thanks, Seth, for the introduction. So I will be presenting sort of a work that's still in progress, and we are still working on it. And it's a work that I'm doing with my supervisors, Seth and Samir. And what we are trying to do is we are trying to learn functions with help of something called as VAEs, which stands for Variational autoencoders. Before we start, like I just want to say, what do you mean by learning functions, or what we are trying to say? So in the general view, you can see there are sort of two different views of when you're trying to learn functions. The one is you say you have got a set of points, and you assume there is a true distribution that is generating those points, and you somehow want to learn that true distribution. So that from those sets of points, you can run a true distribution, and now when you want, so that you can predict the values for some other points that you have not seen. So in here, you're trying to estimate the true distribution. But there is another way also, where what you're trying to say is, you have got different sets of points from different data sets or from different functions. So like you have got 100 different functions, and you have got points from them. Now, you want to learn something that's common between all those 100 functions, so that somehow now when I give you new data sets of points, you can somehow say which is the function that has produced that. So that's the other view. And throughout the talk, I would be generally concentrating on the second view of the functions. So in general, as soon as we talk about learning functions, there's something that comes into mind or that's been used in general is the Gaussian processes. In Gaussian processes, also generally take the first view of learning functions, where you say you have got some n number of points, x1 to xn. Now, you assume that the points that you already have, they are distributed with a Gaussian mean mu x and a covariance matrix sigma x. And the covariance matrix can be just, each element of the covariance matrix can be calculated with help of a kernel matrix between points I and j. And the kernel matrix is generally in Gaussian processes where you inbuild your domain knowledge, or you want to build how your functions or how your things want to behave. And now when you want to do predictions for new points, so in here, f is basically everything that you have. F star are the points for which you want to do predictions. So what you basically say is, your new distributions are also normally distributed, where mu is the earlier mean of this observed data, mu star is the mean of the points where you want to do predictions at the locations, k is the kernel matrix for the points that you already have in observed data, k double star is the kernel matrix for the unobserved points, and k star is the kernel matrix for the observed points and the unobserved points. Standard simple, this way you can use data and estimate points for the new points. So this is standard for Gaussian processes. Like when you don't have any data, you want to estimate functions, like these are like 3 draws from the GP prior, this is what you get. Now as soon as you start seeing some points which are denoted in red in here, you start getting a distribution of functions that can define your data. So stock standard in GPs. Now, all good, you can do a lot of things, it's Bayesian, you can get estimates of your parameters, but there are still few problems. The first is the training complexity of this method is quite high, like it's O(n) cube. And it's not just that the training complexity is high. The problem is also that the prediction complexity is also very high. It's n squared. So like if you had n number of points, even by predicting for only few number of points, your complexity is high. The other thing is which kernel matrix to choose or how to design a kernel requires a lot of domain knowledge, which is good. In general, it's good. Like if you're trying to solve a science problem or something, it's good because people have domain knowledge and you should be using them. But at times, even they don't know how to use it and where to do. And the other thing is, another thing that's lacking in here is, down the line, you're not learning any representation of your functions. You just have a kernel matrix that you're using, but there's no inherent representation or that you're learning. So how can we go around it? Or why we want to do this representation? So the first thing is, we want to learn a representation of our points in some lower dimensions, so that we have an idea that where is the space where all our functions are lying and what they are sharing in between. Once you have got this lower dimensions setting, what you can do is you can use this latent learned dimensions to do faster predictions for the new data points or the points for which you want to do prediction. And finally, the other good thing that can happen with the new learned representation is that you can even go and use standard Bayesian frameworks and do effective samplings, because now you have got a latent dimensions which is generally much smaller than the dimensions of your data. And hopefully, the latent dimensions, your different dimensions are independent, so you can actually do more effective and faster sampling. Now, what we want to do is, let's look at the framework that we are going to use. So the framework is known as a variational autoencoder, which is essentially a deep learning, like it's being used right now in deep learning technique, but rather than first looking at it from the deep learning perspective, we'll look at it from the generative model perspective. And let's see what our generative model is. So what you're saying is, essentially, you have got your data point x. You're saying there is some latent variable z, from which you can, so if given z, I can get a probability distribution of my x. So basically, if I have z's, I can get x. Now, technically, your x has some distribution which is characterized by parameters theta. Now, if I give you z, you can create x. Now, you want to do the inference problem, so you will basically want to do learn the posterior, which basically means you want to learn, this is what I said, we want to learn this internal representation of z. So what we want to learn is p of z given x. Now, this is almost intractable, because if you want to learn it, you will need to calculate p of x. And now if you want to calculate p of x, you will need to do an integral over all possible values of z. And because your z is in real space, you cannot. So the classical way of doing that is, let's let's introduce a variational parameter, which now I will define a new distribution by Q, and I will say that this new Q distribution is going to somehow approximate P, and the Q distribution, because I'm going to choose this Q distribution, I can have nice properties over it. And once I can have nice properties over it, my things become visual. Now when you want to learn this model, you basically want to make sure that your Q is very much similar to P. And the way to do that is basically you can, there are many ways to do it. One of the ways is to take the Kullback divergence between both these distributions. I'll stop here in a way by saying, again, essentially if you want to take a KL divergence between them, that is also not easy to do, because at the end of the day, we said the problem was actually finding this P theta of Z given X. But there are approaches where people have gone ahead and given a lower bound to it. And with help of that lower bound, which people say is elbow, which is known as evidence lower bound, you can essentially estimate Q of phi. Now, the point is how to do that, how to parameterize P, theta, Q. So the people in deep learning world, what they have gone and said is, okay, let's create a deep learning model where what we'll do is, first I'll go for it. So in general, what they say is, I'll just try to say what we mean by autoencoder. What we're trying to say is, essentially we can say this part, P of theta x given Z, is almost a decoder. I give you a latent variable, Z. You can decode it to get the original X. The encoder is the Q part, where you are saying, if I have X, can I get the latent representation from it? So the people in the deep learning world, they said, okay, let's create a big deep network, and those parameters or those distributions of encoders and decoders, they are represented as neural networks. Now, what is essentially the architecture is, you'll say, I have got all my data. I'll pass it through an encoder, which is basically a neural network. This neural network will output a mean vector and a standard deviation vector. It could be any vector, so right now I'm assuming Q to be, the Q distribution that I was taking is a Gaussian. You don't necessarily need a Gaussian. You could have gone and taken a Cauchy distribution, a student distribution. It's up to us. The Q is our choice. We have taken it to be normal in here. And then we can sample from this normal distribution, which will give us this latent variable Z. Now, once I have this latent variable Z, I'll pass it to the decoder. And from this decoder, I'll finally get new X stars. What essentially I want is this X and X star to be very nearby each other. Now, how you can train this neural network is you need a loss function to train. So the way you can train is that you have got, again, this is essentially the elbow that I was talking about. But this elbow has its underpinnings in the variational framework. But if you look just from the deep network or just from a machine learning perspective, you can also see this loss function in this way. The first part is basically giving me the expectation of drawing X given Z under my encoder network. So which is basically saying how good I'm doing my reconstruction part of X and X star. What's the loss that I'm getting from X to X star. And this can be just seen as a regularizer. Now, why KL as a regularizer? I said the underbindings are in the variational inference. So you could have put anyone, but putting KL in there gives you a better grounds of things. Now, the thing is, the standard way of training neural networks is you have a loss function, you use stochastic gradient descent, so you can pass your gradients back to your network, and then with help of the signal from the gradients, you can learn all these neural networks and weights. Now, but there is one problem in here, right? This Z, which is part of my network, is a random variable right now. If there is something random, I cannot backpropagate my errors. So how to do that? Actually, doing that is, again, very simple. I chose a normal distribution in there. I specifically said that you can choose other distributions, student Cauchy, again, because they have this good property, which is known as reparameterization trick, which a lot of people in statistics call as non-centered parameterization. So what we said was essentially that Q will give me mu and sigma. which are basically normal distributions, right? I can also say rather than mu and sigma or this z being random variable, I can say z, let this z be no more a random variable. This be mu sigma, which is always well defined. All the stochasticity of the randomness will now come from an extra auxiliary variable epsilon, which is now normally distributed with a zero and a normal distribution of zero and a zero unit vector distribution. So this way, why you need this is not because it changes it. The thing it changes is it allows you to backpropagate your errors. So this way now you can have large data sets, get your neural network and train it. People have been using this. What they have been using it for is basically they have been passing lots of images to it, creating new images, and once they have got this latent dimensions that we talked about, like the latent vector, they use it to create new images which are similar to your earlier images, but which are not essentially the images that you had, so that you can create new data. But there is another angle also of trying to learn functions is what we wanted to do. So we can actually use the same thing, but this time we want to learn functions. And how we can do that? We can do it very essentially. What we can do is take a lot of functions in any space, use a single variational autoencoder to run over all that data. So because you have assumed that all the functions that you have, they have some common latent dimension where this all can be embedded into. Once you have that latent dimensions, or once you have trained your variational autoencoder, what you can go and do is, now when you have your new points for which you want to do predictions, one simple way is you have your network ready, you can push your data to it, and you can get the function that is trying to do it. That's a point estimate to it. But then, why to just stop at point estimate? What you can do, go ahead and do is, take that latent representation, use that as a prior for the new test points where you want to do predictions. And now, when you're using that as a prior, you can use any off-the-shelf Bayesian tool to use it, and you can sample from it. And again, as I said, sampling from this thing is very easy now because you essentially are trying to create a normal distribution where the dependencies between all your dimensions are very less, so your sampling will be effective and it's going to be cheap. So let's look at an example for a Gaussian process in 1D, how VAE can learn it. So what we first do is, we draw a function f, like there are many functions, we just draw first a single function f from this GP. We take 100 points from that function f, and we train our VAE in it. While training our VAE, what we do is, we basically say, we are going to encode all those 100 points into only 5 points, right? So my data set earlier was like in 100 dimensions, like if I would have been doing any kernel thing or GP thing, I would have been like doing it for 100 dimensions. Now I'm just using it for the 5 dimensions, which is going to be my latent representation, which is essentially a 20 times reduction in my space. And now I can take these samples, I can take many different samples of f from this space and train my VAE over all these functions. Once I have done that, I'll go and now to see whether actually I have learned something or not. Like that's the essentially aim we want to show. So what you go and do is you again draw a new f. Now this is a new f which was not there earlier in any of the functions that I learned, because if I would have used any other function that I learned, then I would be cheating, because essentially I could have stored those things and just spit them out of memory. So you have taken a new draw from there. Now while taking samples from here, you add some noise to there. And now what you basically do is, you take that latent representation and you can use that latent representation as a prior and pass it to Stan. By passing it to Stan, I basically mean is, you have got this latent representation. You have got your decoder network that you said is your decoder, which once given a latent representation, it can create new samples. So that network, you can code in Stan. You have got priors over it. Now just run Stan and take samples over it. And so these are the current results. So as you can see in here, we have very well learned, like the mean is shown in red. So yeah, like this shows that our uncertainties are fine. Even, in fact, we can also see the places where we have got points which are which had a lot of noise, like we have got wider bounds and our functions are fit. So essentially what in theory, what we have said We can use VAs to learn shared representations of function in space. This learned representations are useful because they can help us to do meta learning, and this is what we wanted to do. We had abundance of data, historical data or general data about space. Now, once given a new data set, we don't need to go and need to spend a lot of time in trying to do predictions for that. We can just do like few shots or to do a meta learning in a way that we can transfer our knowledge from the training sets to the test set very easily. And it's not just that we just need to learn the functions. We can actually go and learn different function properties also in this setup, so that when we are drawing our samples next time from our latent dimensions, we can have functions which adhere to the properties that we want to. But there are still few limitations of the current work. One of them is that currently we cannot produce estimates for the points outside our grid. So once we have defined that our grid is within 0 to 100, or like within the grid on which we are sampling on the X scale, we cannot do out of that. So we are working on that how to do that. And the other thing is we are looking forward to extend this technique not to just learn Gaussian methods, but to basically learn more sophisticated models like point processes data, where you can then go and learn the distributions of the times and the distributions in spatial scale. These are some of the references of GPs and VAs. Thank you.
That was very interesting. The question I have is, in your last slides, go back, here, yeah. When you give it this new draw that it hasn't seen before,
yeah,
and Stan goes off, you give it a Stan,
yeah,
right, and Stan produces this functional form.
yeah.
Firstly, what is the cloud around the mean line?
So the clouds are basic. So by clouds you mean the things in gray?
The gray.
Yeah. So those are the different samples that I have drawn from my prior or posterior. Those are basically my posterior draws from these. Those are my samples from the posterior.
Okay. So what has been averaged are all of those?
Yep.
So the red is the average?
Yeah, so red is the average of all of those.
Okay. Now, for someone who is not familiar with this, maybe you could explain what Stan does, roughly.
Okay. So roughly, basically in Stan, what you say is, you specify your model in whatever way you have got your model. So in this case in here, what you are doing is, your model is the decoder network, which is essentially this neural network, which is basically a bunch of neural nets, which is basically factorizations of various weights and biases and multiplying things over it. So this part is my model that is like, so this is the thing that can get from latent dimension to my output.
Probably because I have no picture of that I asked you this question.
Yeah.
Yeah. I have no conception of what that is and how it could produce.
Yeah, so what happens is, again, I have got mu and sigmas. I go and draw a random from n of 0i. I add mu and sigma to that. I pass it to my network. That will give me a range of new x's. I'll do another sample again. I'll do one more sample again. I'll do one more sample again. And all those samples together are the final samples of my model.
Thanks. If you go back to the next slide with the graph on it. With a red graph.
Yeah.
Is there any way of enforcing more smoothness on the function, on your estimated function?
Is there any way of me forcing more smoothness?
Yeah.
There is not. So that's something we are trying to see if I can, but as such, I can't force smoothness from my side. Like, the only way to do that is the other way around, where I can create a class of functions from a GP which are much more smoother and then hope that I'll get more smoothers, but
Yeah, I was thinking you might have smoothed the result using GPs or something like spline smoothing.
Yeah, so I agree, the results with the GPs will be more smoother, but again, the point is with GPs actually doing this thing of learning class over functions is basically what you'll need to do is, once you have got different samples from a GP, you will have to assume that they all are sharing some hyperparameters, and then you will have to train all those GPs together for the hyperparameter selection to basically get a single shared parameter to draw this. So actually doing this thing with a Gaussian process is much more complicated than what we are doing it here, and it's much more computationally expensive also.
Thank you.
Thank you very much, Seth, and thanks for inviting me to this session. The following is joint work with Sam Bat and Seth Flaxman. I would like to start with giving a little bit of background, what kind of problems emergency departments are facing at the moment. There are around 47 people arriving every minute at an emergency department in the UK. Emergency department attendance is increasing at a rate faster than population growth. So the population has grown by roughly 7.5 to 10%, while the attendance at emergency departments has grown by up to 20% or even a little bit more than that. Therefore, there has been the 4-hour target, which has been introduced in 2010 as a measure to try to increase quality of care at emergency departments. And the following graphic shows it quite well. 75% of A&E patients who are eventually admitted to hospital spend longer than 3 hours in an A&E department. 22% spend more than 3 hours and 50 minutes, but less than 4 hours. So staff seems very well aware of the 4-hour target, and they're trying to just shift everyone under the 4 hours. So the goal is that from presentation at an A&E department, from the arrival, before the patient will be discharged or admitted to hospital, that time frame shouldn't exceed 4 hours. There was an article in the BBC just a couple of weeks ago that said that during the year 2018 and 2019, A&E waiting target has been breached by 25,000 people. So all of this leads to massive A&E overcrowding, which obviously leads to less patient satisfaction, increased waiting times, a much higher risk of adverse clinical incidents, and overall low quality of care. So what is the aim of our project? We're trying to understand how it's possible to predict A&E attendance. In particular, we'd like to understand whether it's possible and how well we can actually predict A&E attendance from a time scale of 1, 3, and 7 days. So why are we choosing these time scales? We're working together with clinicians at hospitals, actually, and they said they can have measures like canceling elective surgeries and things like that, or hiring extra staff on a short-term basis. And these measures can take place on a very short time scale. That's why we're choosing 1, 3, and 7 days. We also like to understand the factors affecting forecastability, why people coming in, understand the temporal dynamics of demand, and most importantly, which we shouldn't forget, is we like to understand the operational needs and potential gains for A&E, because only if our work can be implemented at a hospital, it actually does make sense. Otherwise, it will only be descriptive. So this is the data set that we're looking at. We have 8 years worth of data. I'm showing you 4 years here. For both 2 hospitals. One's the St. Mary's Hospital and the Charing Cross Hospital. They're both in West London. And although they're not the biggest hospitals in London, they're fairly big, and they have major trauma units in Western London. St. Mary's Hospital is facing, on average, 224 patients a day, while at Charing Cross, they're roughly 126 every day. And I would like to show you this slide where we are only focusing on St. Mary's Hospital and only attendances in 2017, just as a descriptive first insight into what we could be looking at. So for example, you see a few minima, and they appear in February, April, August. They could be related to school holidays. Then there's an increase over the winter months, from October onwards until kind of almost January, which could be related to the flu season, of course. And then there's a minimum at Christmas, and that's very consistent through all of the years. Then there's one of them maximum is
in July. That's when Trump has been visiting the UK. That could be related because there's been lots of protests and people around. And actually, that's been the minimum. And that's exactly the day when the Grenfell Tower caught the huge fire with lots of casualties. And that's something we first didn't really understand, but clinicians told us later that actually the reason behind this is why, because we thought it should be probably a maximum, is that lots of roads were closed, so people were advised not to go to A&E, or not to these two A&Es. And moreover, lots of people who died, and they died in the tower, they didn't even make it to hospital, sadly. So that's why we have such a low outlier here. Just to give you a bit more insight into the exploratory analysis, there's of course seasonality, as I've just showed you for the example of 2017. As seasonality of the demand, we have again peaks in March, May, July, and winter, and troughs in February, April, and August. This is for the up to since 2015 to 2018. And also there's even different kind of seasonality, obviously. It's the fact of weekdays. You see that there is a maximum on Mondays and another kind of maximum on Fridays, and it's lower during the week and actually quite low on weekends. So on average, actually, a Monday is, and it's 14.8% busier on a Sunday than on a Monday. Having shown you all these insight, which you kind of can see when looking at the data set, we then obviously want to try and predict and make very accurate predictions on demand for the coming days. And we're kind of choosing two different tools. First of all, we're using time series algorithms. A time series is a sequence of data points in chronological order divided into regular time intervals. So you've got dates, you've got your demand, and then you're specifying a time interval that is relating your data. For example, in our case, we've chosen a week because there's high dependence on lag values of 7 days. The same weekdays are quite very much correlated. So just to show you the data's, the time series again. The second approach is machine learning algorithms. And these are quite different in their nature, obviously. They learn from the data through pattern recognition and inference from sample data. So instead of kind of only feeding it dates and demand, we're also doing something which is called feature engineering. So it's been much more creative because you're choosing the features that you're feeding into the algorithm and then see how you can actually tweak this around. So for example, this is the model matrix that we've been using for our analysis. And there's obviously the demand on the day. That's the demand that we want to predict. And then the feature that we're feeding it is the month. In this case, I've chosen the example of April. There's yesterday's demand. Then there's the demand on the same day last week, the average demand of the previous week. Then there's a feature for time, which is just linear across our time series. There's bank holidays and school holidays, the weekday, and then there's some weather data which we've taken from weather stations around London, which are close by. So rainfall, maximum temperature, minimum temperature. And then as a last bit, we are also using flu hits on Google. So if someone typed in Google on that day, didn't type in Google, types in flu on that day, we have a measure for that. And these two approaches are very different in nature, and the challenge is actually to evaluate them and combine them in the right way. So how are we actually doing this? So this is kind of our unified approach to the evaluation. First of all, the time series algorithms, that's kind of the first step. We're using 6 years worth of data, and then we use 1 day temporal cross-validation. That's because we've got a chronological order in the data, so we're validating them on a set for always 1 day on a test set of 730 days, so roughly 2 years. Then the machine learning algorithms are a bit more involved, and the big difference here is that we have to adapt the procedure because the machine learning algorithms require tuning of the hyperparameters. So in this case, we're using 4 years worth of data, We train the algorithms and tune the higher parameters on another set of 2 years with 1 day temporal cross-validation, and then we fit the model on 2 months of the test data. So this describes the model again, like there's kind of an inner and outer loop. So we've got 6 years worth of data. Then that goes into 4 years of an initial training window, 2 years of temporal cross-validation, and then we fit it on the test set for 2 months, and then we move shift the whole sets 2 months further. Last but not least, we're not only using simply the time series and the machine learning algorithms, we also use an ensemble approach. In our case, we're using stacking. So the idea of stacking is to train a learning algorithm to combine the predictions of several other learning algorithms. So all the algorithms that we fit already to the data and their predictions, we're fitting another algorithm. In our case, it's a linear model onto the predictions to make or try and make even better predictions. And we're using temporal cross-validation in that case again. And these are our results. So these are 1 day forecasting results for either St. Mary's Hospital and for Charing Cross Hospital. And these are the algorithms we're using. So there's several time series algorithms and the machine learning algorithms. And as you can see, there are the 2 random forests here and here, which give us a percentage error of like roughly 3%, 3.2, 3.3%. It's similar for the Charing Cross Hospital, it's 3.9, and it's, 3.9% for the random forest. The current method that the hospitals are actually using is they're just calculating the average of the last 6 weeks worth of data. And that's a 6 weeks moving average. So, and they're achieving like an error rate of 8% or 11%. So we're actually doing much better than that. We have very similar results for 3 and 7 day forecasting. Again, we're getting like a 3.2% and a 3.3% error rate here. So the conclusion is our predictions, we predict up to like plus minus 10 patients better every day. And doing some naive kind of estimates, one could say that that St. Mary's Hospital in particular could save up to £300,000 every year if they used our method instead of the 6-week moving average method. What are further steps of this project? We would like to obtain more historical data at a higher resolution, like ideally like hourly data of demand. So that also, if this will ever be made like a tool for clinicians that they can actually use, they can update it on an hourly basis and see if something happens. Also, we would like to obtain patient-level data to understand like routes of admission. So who do patients see? Which routes do they go? When are they going to? When will they be discharged? And where do waiting times increase? Or where are they waiting? And then what brings people to A&E and whether their visit to A&E is actually a priority. Explore other indicators, flu tests and data from neighboring hospitals, because obviously hospitals influence each other. That's what you could have seen for the example of the Grenfell Tower. And we'd like to, in the end, implement it into a tool which also allows clinicians to have some kind of way of quantifying the uncertainty of how many people will be coming. Thank you very much for your attention.
Hello, hi. Thank you very much for presentation. It was very interesting. I'm over here, sorry.
Couldn't find you.
Just a couple of very quick questions. I was very interested to see that you took this data on how many times people have been searching for the flu on Google. Is that, first of all, do you have any insight of what's the relationship? Did it actually come out to be significant that, the higher the percentage of, the number of hits on Google on the day, the higher the number of admission? And was that regional data, as in only searching or hitting Google, I don't know, from IP addresses in London, or it was generic UAK. And the other thing was whether there was any lag, as in, if I search for the flu tonight, I might go to A&E tomorrow morning, and or in 2 days' time. So whether you looked at any of the lag effects.
To your first question, it's all of the hits across England. So it is a very wide area, obviously. It's not just London. And then the flu is obviously something that appears more in winter months. So across the year, there are not many hits on Google. And therefore, it's also correlating very strongly with the type of month that we're having in our matrix. So it does make an effect, but it's not the greatest effect. So we might think about using other hits on Google. I'm not sure what else one could really use, but to explore that field a bit more.
Thanks. Hi. I'm Chris Maney. I work for a hospital in Birmingham. Obviously, I think that's really interesting and directly applicable to our service and many other people's. One of the things that's really difficult with A&E data on a national level is that the waiting time gets truncated just after the 4 hours. So because there's no further incentive to record the later time, it just disappears. And in general, as the data quality trails with time once the target's gone, you're obviously modeling on just 2 hospitals there, and you obviously have waiting time longer than that to get the figures you have. Do you have any feel for the training set sort of data quality issues? Is there anything that's a real difficulty in proposing this type of model?
So as of now, to be honest, all the data we have at the moment is the dates and the demand on that day. We don't have any more data. We're working on that at the moment. But there is a real issue about waiting times also, because often I think there's a real increase of people that are admitted just under 4 hours. They've been admitted, then they're out of the system, they don't have to record the waiting time anymore, and they're kind of safe, and then they will be discharged an hour later. So there's definitely a problem there, and I think that will be a problem we'll be facing very, very soon, hopefully, when we get more data.
Okay, thanks. So I'm conscious of the fact that this is the last talk, and so everybody should be totally trashed. And also, I'm not a statistician. I'm going to talk really about computation. But computation, I think, is, I look for enabling computations that will allow us to do things with data that we couldn't before. Like backpropagation sounds like such a trivial thing, but it's really been an enabling technology, right? We've got we've gotten enormous play out of it. And so I'm going to talk about a trick related to backpropagation, which I hope might be useful, and maybe you can help me with that. So, but just to make sure that people have something to take home, I'm going to start with a crash course in automatic differentiation. And maybe this will give you, if you already know what automatic differentiation is, if you're really familiar with it, maybe this will give you a different perspective on it, because there's a bunch of different ways of looking at it. So, whoops, how do I go to the next slide there? Next. Okay, so crash course. If you have a primal computation, and sorry about the notation, this is programming language notation where we write things next to each other for application, like applying a matrix to a vector, right? That's applying a function f to a value x. Okay, like sine of x, right? It's very mathy, isn't it? Yeah. Sorry about missing the parentheses. Okay, so we have a primal computation, y equals f of x, and as you'll recall, that if that's a numeric computation, so x and y are vectors, then there's a Jacobian of f. And we can ask if now let's say that both x and y are very high dimensional. So we're not going to be calculating any big Jacobians. We're not going to be calculating any million by million Jacobians, right? But if we have a perturbation of x that induces a perturbation of y, and you get that by multiplying the Jacobian of f by x, and that gives you the consequent perturbation of y. And similarly, or adjointly, if you have a gradient of something with respect to y, and you'd like to know the gradient of it with respect to x, you can take the gradient of it with respect to y and multiply that by the Jacobian transpose to give you the gradient with respect to x. And in the interests of not having all these unwieldy nobblers, when I'm talking about the gradient of something with respect to some variable, I'll use a backtick on top of that variable, like these graves here, right? Okay. So here's the Folk theorem of automatic differentiation. You can take any numeric computation, and you can mechanically transform it So like not requiring any creativity, right? Mechanical process, like a calculus, to also propagate derivatives with a small constant factor overhead. So that's what the difference is between just, like taking derivatives like Newton did. Yeah, because here you want to take a derivative of a computational process, and so complexity comes into it. And so the Folk theorem of AD is that you can do it with only a small constant factor overhead. And there's actually two main kinds of automatic differentiation, although there's a gazillion other kinds. It's a really rich field. It goes back to the dawn of the computer age. The very first PhD thesis in computer science was in the 50s, and it was on automatic differentiation. Right? So it's actually a pretty broad field. But OK, to grossly caricature, right? If we have, so here's an operator. Oops. Okay. So there we have this is a forward transformation operator. And we can apply that to some computational process. And then you feed into to that not just the original thing, x, but also a pair. So you pair that with a perturbation. And then you get out of this the primal output and also a perturbation. So that's forward automatic differentiation. And this is reverse automatic differentiation. And this one is forced to be a staged computation. This is like the big pain in the rear with automatic differentiation, right, with backpropagation, which is f of x has enough information in it to tell you the Jacobian. So if you want to do this reverse transformed, it's going to have to take something that's the gradient with respect to the output and bring that back to the input, so that's going to have to be a second stage. So you have a forward phase, it's called, where you do this. This gives you the primal output and also a back propagator, and then you apply that to a gradient with respect to the output, and you get a gradient with respect to the input. Okay, now I personally have done like a lot of work on generalizing this to higher order types, on like lots of things that I think are really interesting that I'm not going to talk about today. But they are relevant to Stan and stuff like that. So they're right, they're not irrelevant to statistics, but it's not what I'm talking about. What I want to talk about today is a new mode. So okay, so here's the big trick to get AD to work. And basically, right, you're going to derive like it's 1699, yeah? So if you have a composition of two functions, well, there's the chain rule. And we need to tweak the chain rule to make it work well for us. If you just take the chain rule naively, it doesn't play well with computation because it's not symmetric in the two things that you're chaining together. But if you make tuples, then it works. So here's how this forward operator works. You've got this function, and you're bumping it up so that every real value is paired with a perturbation of that real value. And that then has this property. This is called compositionality. Okay, and this is the numeric result. Okay, so what's nice about something being compositional is that it plays well with compilers. So if you have a programming language compiler, you can dive into it. It can dive into the code, and if it's transforming like lots of functions, if the transformation is compositional, it can go in and bottom out on the individual functions. So the transformation of the whole big program just depends on the transformations of all the individual little basis functions. They're called the library functions. Okay. And plus the transformations of glue, like latting and stuff like that. But that's beyond our scope here. Okay. So now let me talk a little bit about getting reverse AD from forward AD. And then I'll talk about this new inverse mode. Okay. So because the forward transform is compositional, we have this equation, right? That's just what I had on the previous slide, the definition of compositionality, but I've applied it to a particular argument there. And this is the numeric value you get out. This is this asymmetric kind of chain rule, right? Because I've got an f of g there, whereas just a g there, so not nice. But okay, so numerically, this is what you get. And that means if you apply it to a big composition, so let's say I have this big chain of a whole bunch of functions applied to x, which is, after all, when you run a computer program at a point, like at a particular input, that's all you have, right? Like there's a sequence of, right, if all you're looking at is the numeric values, then all that's happened is a whole bunch of numeric functions got run on some vector numeric values, and you got one out at the end. So this is like a computer program evaluated at a single point, and like we've stripped away all the control stuff because that got resolved. Okay, so then we can ask, well, if we apply this j to this whole big thing and apply compositionality, and then just take the second element of the tuple, then you get this. So where each of these little Jacobians, it's a micro-Jacobian, is just a Jacobian of one of these little steps of the program. And if you want to convert this to, if you want to derive reverse AD from this, then you just you reassociate, right? So you associate it this way, and then you say, okay, well, look, we've got this output perturbation is this big thing, like this product times the input perturbation. Well, I can just take the transpose, and so then I've got this rule. So there's the gradient with respect to the output. I get the gradient with respect to the input. I get this, and then I apply that transpose, and I do another associative rule, and I get this. And notice that this is going from the end of the computation back to the beginning, and that's a big pain in the rear, because you have to remember all of the intermediate values, at least some of them, in order to apply these in the reverse order. Okay, that's AD. Any questions? All right, so if you were a compiler person now, presumably, you could go off and you'd say, well, maybe I've got to work out some details, but I could go build a compiler to do that. But now let me talk about a new mode that we can quickly derive in this context. So let's let these individual transformations, these individual functions be state transformations. So I'm considering the x to be a machine state, a big vector of all the variables, right? All the live variables, the whole memory, yeah? And so then here's what one such f looks like. Well, it's some basis function. And let's just consider really simple basis functions like, sine and exp and plus and times and stuff like that. So little unary and binary ones. So here you've got the machine state at time I minus 1, and here's the machine state at time I, and all that happened is two values, this one and this one, got run through some kind of well, sorry, this is a unary function. So this value got run through a unary function yielding that value, and everything else stayed unchanged. And similarly here, this is a binary function. So these two values got fed into some binary basis function yielding this value, and everything else just went through unchanged. So if we look at the Jacobians of those things, they look like this. They're very simple, right? So here's the Jacobian of one unary function, right? So the rest of, so everything's all ones, right? Because most of the memory is left unchanged, except the output L. So that row has something else on it, and it read the value, this R. Yeah, and that's the derivative of that unary operation at that point. And this is the same thing for binary operation. Okay, so now here's the big thing. Here was like our big insight, which is those Jacobians have trivial inverses. So usually, for doing forward and reverse AD, you notice that multiplying by those matrices can be done trivially, right? Very, very quickly, using just a couple operations, but multiplying in place. But if you look at them again, look, they have trivial inverses. Okay, well, that's not quite true, because this has a 0 column, so it doesn't have a trivial inverse. It doesn't have any inverse, yeah? And the same here. But if you require the output of this unary operation to be the same, so Li and Ri have to be the same. So you can only update a value in place. And this binary operation, its output has to write over one of its two inputs. Then these matrices are not singular, and they have trivial inverses. And so you can do the following to develop a new automatic differentiation mode. And so here's the trick. Well, we'd like to solve the Jacobian times x prime is equal to y prime for x, where j is the Jacobian of some arbitrary computation. And we'd like to do this efficiently. So you think of x and y as both being million dimensional, right? So you're not going to be constructing this linear system. Now, would that be, and similarly, you might want to do it for Jacobian transpose, because Jacobians aren't necessarily symmetric. Unless it's the Hessian, in which case it is, and the Hessian is from nesting, but okay, I'll second that. All right, so can people think of anything that this might be useful for? Well, the obvious thing is a Newton step, right? So, so this would let you do very fast Newton steps in high-dimensional systems. That would be kind of cool. Okay, so what's the trick? Well, here's our solution. We're trying to solve our x prime, so that's the Jacobian inverse times y prime. So you write it out, and write it out, and okay, look, what do we get? You take, so you've got your target perturbation of the output of the computation, and you want the input perturbation that would cause that output perturbation, right? And so you take the target perturbation and you multiply it by the Jacobian inverse of the last operation of the program, going all the way back until the Jacobian inverse of the first operation of the program. Okay? And there's a similar one for if you have a target gradient for the input of the computation. You want to know what gradient at the output of the computation would have caused that, would have induced that. That's a little bit funnier. I don't know how useful that would be. But anyway, you get both of these. And what's fascinating about these is that they're exactly structurally the same as conventional forward and reverse AD, except that the roles have kind of gotten reversed, right? Because usually in forward AD, you talk about multiplying by the Jacobian. In reverse AD, you talk about Jacobian transposes. In forward AD, you talk about perturbations. In reverse AD, you talk about sensitivities, gradients. And here, this forward thing is manipulating gradients, and this reverse order thing is manipulating perturbations, and that's basically because reverse, right, transpose and inverse both kind of flip the matrix around, right? Both switch input and output roles. Okay. So these are these new modes of automatic differentiation. And we have a toy implementation. We haven't used it for anything interesting yet, but the reason I thought I'd talk about this here is I hope you guys might have some uses for something like this. And if you can think of any, like a high-dimensional system where you'd like to multiply things by the Jacobian inverse, please come talk to me. Okay, and let me close by first saying that I have a collaborator on this work, Jeff Siskind. Anything tricky or difficult, any implementation, any hard math, he did. This is work in progress, obviously. So there's one constraint about this, right? If we go back here, in order for these matrices to have trivial inverses, they have to be square, right? That means the number of live variables has to stay constant. That means it has to be a constant with computation. That's a pretty severe constraint. Now you can try to relax that constraint by doing tricks, but okay. There's one kind of computation that seems naturally to meet that, and that's shooting problems. So you have an ODE, and you have an output target, and you're trying to figure out what input to the ODE will meet that output, like a very high dimensional. This seems to be good for that kind of thing. All right, and let me just close by saying that we thought this was totally original, but when we carefully looked at the literature, people thought of this basic idea before, but they did it in a different framework where you can't do it automatically and blah, 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 but that's our bias talking, right? Because numerically it's identical. And you could if they'd kept working on it, if they'd kept pushing on it, they would have gotten it automatic like we did. Okay, thank you.